Okay, picking up where we left off last time, we had calculated ion concentrations because we're talking about solutions. And solutions, of course, are where you've got something mixed into another thing, and typically that's a solid or a gas or a liquid mixed into a liquid. That's primarily the focus of our solutions, at least in this class. And when you make solutions, it's often convenient to store your solutions in concentrated forms, high concentration forms of your solutions. We typically call this stock solutions. Stock solutions in the lab get stored in the stock room. It's a room for storing solutions and chemicals. So many lab procedures call for less concentrated solutions. Usually it's stored at the maximum concentration or close to the maximum concentration, and then you just dilute it down when you want to use it. So they need to be diluted down to the required concentration. And we can do this. You just take a certain amount of your stock solution and add water. It's relatively simple. Or some other solvent if water is not your liquid or your solvent. So there's this very nice, helpful, handy dandy equation for solution dilution. So to determine how much of the stock solution to use, we're going to use this dilution equation. What kind of equation is it? A dilution equation. So what sort of things do we think we might use this for? Dilution. And that's the only thing that we're going to use it for, because otherwise you will lose points on your final exam, because that's when this material will show up for the first time. The only context in which we can use this is dilution. You might see some people online using a formula that's either this or it looks very similar to this, and I don't like that. This is one of my weird hills that I'll die on, presumably at some point, maybe when I'm old and frail, that M1V1 equals M2V2 should not be used for anything other than solution dilution. The problem is that it will sometimes work for solution stoichiometry. That's the trap. I'll show you how that trap works. So M1 and V1, M1 is capital M, so that's molarity. V1, capital V1, is the volume. This is for one solution. So for example, this might be the stock solution. It doesn't have to be the stock solution, but this might be your stock solution. And then M2V2 might be our new solution. So it's similar to our simple gas law, Boyle's, Charles, Avogadro, Gay-Lussac, all those sorts of things. What's most important is that you get your numbers matched up. Your M1 and your V1 have to be for the same solution. Your M2 and your V2 also have to be for the same solution, but the other one. And the reason that this equation works is because if you take molarity times volume, it gives you moles. And since we're just diluting it, we're just adding in liquid, we're just changing the amount of space that it takes up, the moles are just more spread out in the dilute solution. So it's the same number of moles, nothing's changed there. So just as one more reminder, I'll probably remind you more times, only use this for dilution. When you need to do dilution, this is a super helpful equation. It's awesome, it's so fast, it's so easy, it's even breezy. For anything else, oh look, there I put more information about that. This applies to only solution dilution, not stoichiometry. So don't use it for stoichiometry. Don't use it when there's multiple chemicals involved, like we're reacting chemicals together. Only for diluting. As a lab safety note, generally when you're diluting acids, you want to add the acid to the water. Acids release heat when they mix, just kind of generally. So the reason for this, acid to water like you oughter, not the furry riverine animal, but ought to, acid to water like you ought to, is because if you add water to a concentrated acid solution, it's the acid part, not the water part, that releases all of the heat. It's because it's dissociating. So when you add water to a concentrated acid solution, that has the potential to release a ton of heat, and then you could cause your solution to boil, and then maybe you get splashed with acid that's like boiling hot, or you smell acid vapors and they condense in your lungs. And then you've got acid pneumonia. I'm just kidding, you wouldn't make it that far. I don't know. It would be bad regardless. Okay, so how do we use M1V1 equals M2V2? This is a perfect example, or it's an example. I'm not going to say that my examples are perfect. So M1V1 equals M2V2. We have the question, how much 6 molar sodium nitrate solution should you use? How much being our question, to make 0.442 liters of a 1.2 molar sodium nitrate solution. So this 0.442 liters, this 1.2 molar sodium nitrate go together. We'll call those M2 and V2. So M2, 1.2 molar. V2, 0.442 liters. And then 6 molar must be our M1. So that means that we are looking for V2. If we're looking for V2 in this equation, we need to move the M2 to the other side. So divide both sides by M2. M2 gets canceled out on the right side and appears on the left side. So V2 is equal to M1V1 over M2. And we have all of those variables, so we can just plug them in. So we're solving for V1. All right, change the labels. Spoiler alert, it doesn't really matter. Okay, M1, 2, V2, course correcting. The end result is the same, the labels I just had flipped. Okay, we have all of those things. So 1.2 molar times 0.442 liters over 6.0 molar. And the molarities cancel, and we are left with liters. So 1.2 times 0.442 divided by 6. We get a value of 0.088 liters of 6 molar sodium nitrate. So if we wanted to make this 0.442 liters of 1.2 molar sodium nitrate, we would take this 0.088 liters or 88 milliliters of our 6 molar solution, and we would dilute it up to a volume of 0.442 liters. And then boom, it's 1.2 molar. It's a relatively quick calculation, especially if you don't screw it up like I did. Questions about using our very fun, very cool, very handy dandy solution dilution. Cool. So if you're doing dilutions, oftentimes you won't be doing it to like weird numbers like 0.442 liters. A lot of the time it's going to be using volumetric flasks. And volumetric flasks are great for one single particular volume. And so the way that you use a volumetric flask is you would take some out of your concentrated solution, you would add it into this other flask, and then we're going to fill this up to the mark on the neck, and then that means that it'll be at whatever the volume is, maybe half a liter or a liter or a quarter of a liter or whatever volume you have it. You add that stock solution to the volumetric flask, and then you add the deionized water until it reaches whatever the calibration mark is on the neck of the flask. And then stir it at some point. And then you'll have the molarity of the solution that you want. I can show you that in lab if you're curious how that works. Oftentimes when we're doing reactions with aqueous reactants and products, we'll typically specify our amount of reactants or of products in terms of volume and concentration. We have primarily been doing stoichiometry with grams and molar mass. And molar mass. We've also done it with gases, in which case you would have more variables. So volume and mass are kind of analogous in these calculations, and concentration is our conversion factor, similar to how molar mass is. We can use volume and concentration to calculate moles of a reactant or product, and then we do the same stoichiometry that we've always done. It's the same steps. The stoichiometry part has never changed. It's always been the same. It's just that the volume and the concentration to start the problem is new. Here's what a general solution map might look like if you want a general solution map. So we would be starting with some volume of a solution. You multiply it by the molar concentration of A, since molarity is moles over liters. So if you multiply moles over liters by liters, you just get moles out. That gets us to moles of solution A. Then we would use the molar ratio from our balanced chemical equation that we're either given or we come up with. And we can figure out how many moles of solution B we would have or need or create, whatever the circumstances are. And we can use the molar concentration or the volume to figure out the other one. So we might end with molar concentration. If we're given volume, we might end in volume if we're given molar concentration. So there's like still some ways that we can switch around this solution map, but this is one possible configuration that you might see. The front end is pretty much always going to be the same if we're starting with a solution. You can also start with grams, go to moles, and then end up with solution stuff at the end. This is part of why chemistry is, I think, really difficult, because there's a lot of ways that we can change it. All right, let's look at an example. What volume of a 0.500 molar sodium sulfate solution will react with 275 milliliters of this concentration barium chloride to completely precipitate? What does that mean? All barium 2+ in the solution given the balanced chemical equation. And we're even told that it's balanced. If we weren't told that it's balanced, we could also tell that it's balanced, probably because there's coefficients. Usually if there's coefficients, it's already balanced, so we don't have to do that. What are we finding in this question? We're finding volume in liters. We know that we're finding volume in liters because it's right next to our question word, what? So we're finding volume in liters of a sodium sulfate solution. So we're going to end up with liters sodium sulfate, and this is the slide. This is the one. It's wrong, and I forgot to change it last semester. Okay, that's the wrong balanced chemical equation. Don't worry, we'll come up with a new one. All right, perfect. We've got our brand new balanced chemical equation. You too could become this fast if you wanted to and if you needed to for your job. Okay, so now it's actually sodium sulfate now, and it's barium chloride, and barium sulfate here is our precipitate. So we are trying to find volume in liters, sodium sulfate. The other chemical that we were given is barium chloride. So we are starting with barium chloride. We were given a volume, and we were also given a concentration. So we are going to be starting with milliliters of barium chloride, and our goal is to get all the way over to liters of sodium sulfate. So we have to switch chemicals. The chemical that we started with is not the same chemical that we are ending with. That means that we have a stoichiometry step. There has to be a stoichiometry step to switch chemicals. The milliliters to liters, there's some other stuff that will be involved in there. A great place to start here would be converting to liters of barium chloride. I think this is probably where most people will start. So we'd be starting with our 275 milliliters of barium chloride. We convert that to liters by dividing by 1,000. It turns into 0.275. In order to do stoichiometry, in order to change our chemical from barium chloride to sodium sulfate, what units do we have to have? To use this balanced chemical equation, what units do we have to have? Think of our friend who comes and joins us for all of our exams. Moles. We need moles. Moles is the unit that we have to use a balanced chemical equation. So we have to convert from liters to moles. We'll get to moles of BaCl2, and then we can get to moles of Na2SO4, and then we can convert to liters of sodium sulfate at the end. We need moles to use balanced chemical equation, aka ratio. Just as a reminder. Okay, so we've got our liters. We need to convert to moles. To convert from liters to moles, we've got molarity. Molarity is secretly moles over liters. So taking our 0.275 liters BaCl2, if we multiply by our molarity, the liters cancel, we've got moles of barium chloride. So 0.0675 moles BaCl2. What is our ratio between barium chloride and sodium sulfate?
1 to 2.
Why is it 1 to 2?
Sorry, it's 1 to 1.
It's 1 to 1. So if we look at our balanced chemical equation, right, we've got nothing in front of either, so it's a 1 to 1 ratio. So the barium chlorides cancel, and we get sodium sulfate. We've got moles of sodium sulfate, and then to convert to liters at the end, we have to use our molarity. And remembering that molarity is moles over liters. We have moles, and we're trying to get to liters, so we're going to divide by our molarity. Or you could also use some variation of the chemical formula, not the chemical formula, the equation. Maybe I didn't plug myself into charge last night. Okay, so we're going to divide by our molarity. the moles cancel, and we'll be left with some number of liters. Zero 0.1375. We would round that for 3 sig figs, liters, sodium sulfate. Questions about any of the individual or particular steps? And it was a little bit of a rotary way of getting to the answer. Rotaries are what they call roundabouts in other parts of the country. Logan's not invested in he doesn't have the same amount of skin in the game, so he gets to laugh at my jokes. Okay. Who remembers the equation that we can use for one very specific purpose? Starts with M1. M1V1 equals M2V2. I am now going to show you the trap of M1V1 equals M2V2. If, and this is something that you shouldn't do, I'm showing this to you as a warning. Word of caution, word of warning, caution, danger. Okay, so if we make this 275 milliliters our V1, if we make this molarity our M1, and if we make this molarity our M2, we can find this volume with M1V1 equals M2V2. This is illegal. Do not try this on the final exam. Okay, so M1, 0.250 molar. V1, we're going to convert it to liters, 0.275 liters. M2, 0.500 molar. V2, question mark. V2 equals M1 V1 over M2. So that means that we are going to put 0.250 molar times 0.275 liters over 0.500 molar. The molarities cancel, and we should be left with the same exact number. So 0.25 times 0.275 divided by 0.5. We get out 0.1375, round it for 3 sig figs, liters. This is the problem. It works sometimes. The only reason that this works is because we have a 1-to-1 ratio. If you do not have a 1-to-1 ratio, you will get the wrong answer 100% of the time. Every single time. So that's why you should not use this. Do not do. Do not do. The thing that we are missing with this M1V1 equals M2V2 is we're missing this stoichiometry step. So nowhere did we correct for the fact that we were changing from barium chloride to sodium sulfate. And it just happens to work out because it's 1-to-1. Happens to work number-wise, numerically, because it's a 1-to-1 ratio. If it's not a 1-to-1 ratio, you get the wrong answer 100% of the time, guaranteed. Okay. Exercise. I'll give you some time to work on this. We haven't actually talked about acid-base neutralization reactions yet, so I'll give you the balanced chemical equation for this. What was that? Okay, a 25 milliliter sample of nitric acid solution requires 35.7 milliliters of that concentration of barium hydroxide to completely react with all of the nitric acid in the solution. What is the concentration of the HNO3 solution? Give you a little bit of time to work that out. Okay. What are we finding? Concentration of HNO3. Concentration often, not always, often has units of molarity, moles per liter. We were given volume and concentration for barium hydroxide. So that's the one that we're going to start with. Because we've got both the things that we wanted, so we're going to start there. Both the things we need. More variables for barium hydroxide than for nitric acid, so we're going to start there. It may be helpful, it's not actually necessary in this case, but it may be helpful for you to convert the milliliters to liters. So 0.0357 liters. If you have trouble converting between milliliters and liters or with kilo prefixes, Logan would be more than happy to help you out with that during his SI session today from 3:30 to 5:30. Or during lab, that would also work. Okay, so we've got that many liters. Our chemical is barium hydroxide. We were also given the concentration. Molarity is moles over liters. So if we take molarity times liters, that will give us moles. And we need to get to moles. We need to get to moles because we're starting with barium hydroxide and we're going to nitric acid. We're switching chemicals. That means we're going to have a stoichiometry step. And when we're doing stoichiometry, we have to have moles. So times 0.1508 moles per liter. And this will give us the moles of the barium hydroxide. Zero point 0.00538 ... moles barium hydroxide. What's our ratio between barium hydroxide, the thing we have, and nitric acid, the thing that we want? 2 to 1. 2 HNO3 to 1 BaOH2. We're going to nitric acid, so 2 HNO3 on top, and the 1 BaOH2 on the bottom. This cancels the chemicals. So times 2. This is the number of moles of HNO3 that we have. We're trying to find concentration. Concentration is molarity. What's molarity equal to? Moles over liters. We have moles. We were given liters, milliliters, but we can convert that. So if we divide by 0.0250 liters, this will give us the molarity. 0.431 molar HNO3. Questions? Just as a note, M1V1 equals M2V2 gives you the wrong answer. So don't use that. Another note, you can actually leave this in the volumes. You can leave them in milliliters since they're both milliliters. The milli prefixes will just carry through and then cancel out at the end. So if you want to do that, if you're algebraically savvy, you're welcome to do so. Otherwise, for the rest of us, probably don't do that. Okay. A place where we frequently use solution stoichiometry, that's the stuff that we were just doing. Solution stoichiometry is often applied in a lab procedure called a titration. What we are doing in a titration is we're taking a substance with a solution of known concentration, so like a solution that we made up. We know what the concentration of the chemical is. We're going to add that to another chemical that we don't know what the concentration is. And we put in an indicator so that we can tell when the reaction has completed, when we've reached that stoichiometry point. And then it changes colors, and then we can figure out, based on how much we added, what's the concentration of our unknown. Our net ionic equation for acid-base titrations is typically H plus OH minus goes to H2O. We'll learn more about why H plus and OH minus are important in the next chapter. So here's an example of an acid-base titration, just part of it. So this is going to be our HCl solution. What we're representing here with the white bits is the H plus that we saw in our net ionic equation. So we're just going to show the H pluses here in this solution. We'll also have the OH minus that's now showing up in this solution. So the OH minus, the hydroxide, is in this piece of glassware. This piece of glassware is called a burette. And burettes are really cool. They're great for titrations. They're not really good for much else. Burettes have labels on them. It starts from 0 at the top and it goes down, the ones that we have at least, to 50. And so it tells you how much solution has been added. So it measures the added solution. So the numbers on there are set up in such a way that it's easy to tell how much of our solution that we've added into our flask. In our flask down here, we've got our H plus, and those react. We also have an indicator. The indicator turns pink or fuchsia when it reacts with base. So once we have a little bit of extra of our base, we've used up all of our H plus, then the indicator will turn pink. It's the same indicator that we're going to be using in our acid-base titration lab. So we start off initially, we've got our known concentration up here, we've got our unknown concentration down here. We just start adding in our base into our acid. And these react and they form water molecules. And so that uses up some of our H plus. We continue adding solution until it stops and turns pink. The closer that we get to this pink endpoint, the longer there will be pink swirls kind of floating around in solution. The longer those will stick around and then eventually disappear. And then once we hit this pink indicator point, it's going to stay pink basically forever. Not forever, but basically forever. We're not going to stick around for them to turn back. Our equivalence point is usually signaled by an indicator, and you can thank your lucky stars that we're not going to be doing a spelling test for the class. Our indicator that we typically use is phenolphthalein. And People often don't like spelling this word, but it's really fun. That's phenolphthalein. It's cool. Turns pink in basic solution. There are other indicators, but phenolphthalein is the one that we typically use. All right, some real-world examples. Sodium hydroxide added to an HCl solution. That's what we were doing with that burette in that titration diagram that I was showing you. When the sodium hydroxide and the HCl reach stoichiometric proportions, when we've got 1 mole of OH for every 1 mole of H+, the indicator will change to pink. Ideally, we would be stopping at this light pink endpoint. We don't add very much of the phenolphthalein, and so it's pretty easy to just breeze past this light pink endpoint and go to a dark pink endpoint. Once it hits this dark pink color, it will not get any darker. So you don't know, if you get to this dark pink endpoint, you wouldn't know necessarily that if you've gone 1 drop over, if you've gone 10 milliliters over, if you've gone 4 liters over. There's no telling how far over you've gone if you get to this dark pink endpoint. So if you stop at this light pink endpoint, that's ideal, but there is some luck involved in that, as we'll see in 2 weeks during our lab. Okay, the way that we can use this in calculations is basically the solution stoichiometry stuff that we've done before. We don't really actually need to know how to do the titration to be able to do calculations with the titration. So we've got a slight switch up of the types of solutions that we were doing previously. We are looking now for the mass of calcium hydroxide if it's titrated to its equivalence point. The equivalence point is when the H+ concentration equals the OH- concentration. Basically, all we're saying with this equivalence point is that we can use our stoichiometry. We can use the ratio from our balanced chemical equation. That's kind of all that that's there for. And it took 44.02 milliliters of this concentration of HNO3. We've got 2 variables for our HNO3. That's the chemical that we're going to start with. So 44.02 milliliters HNO3. We need to use this with our molarity, and we need to remember that molarity is moles over liters. Since it's moles over liters, we need to convert from milliliters to liters. So we divide by 1,000 to convert to liters, and we get 0.04402 liters HNO3. We can use this liters with our molarity. We multiply, and this will give us the moles of HNO3. So 0.04402 times 0.0885. We've got a relatively small amount of moles of HNO3. Rewriting this over here on the left side. Our goal is what? What are we trying to get to? Mass. Mass is going to have units of grams. Of what chemical? CaOH2. So we need to switch chemicals from HNO3 to CaOH2. We are already in moles, so we can do that switch. To do that switch, we need our ratio from our balanced chemical equation. It's 2 to 1. So we have to put in 2 HNO3 to react with 1 CaOH2. So we're dividing by 2 in this case. The HNO3s cancel. This will give us the moles of calcium hydroxide. This is one of those alternate endings / beginnings that I was talking about before. So now instead of going from moles to liters or moles to concentration, pointing the wrong way, we're going to grams. To get from moles to grams, moles to mass, what do we need? How do we convert between grams and moles? Molar mass. We're still using it. Can you believe it? After all these years. I guess it hasn't been years, it's been months. But yeah, we're still using it. It's still coming back. And we have a molar mass of 74.094 grams per mole. You will be expected, especially on the final, to be able to come up with a molar mass. So there were 0.144 grams of calcium hydroxide. Questions? Okay, for time's sake, I'm going to skip this one. So that we can get on with freezing point depression and boiling point elevation. So these are two terms. These are called colligative properties. Colligative properties are a type of property. They depend on the number of particles and not on the type of particle. So normally colligative properties are a little bit unique in that way. It simply depends on the number of particles. It doesn't depend on the type of particles. You've probably interacted with colligative properties whether you knew it or not. One of the common uses of these colligative properties is if you add a non-volatile solute to a liquid, it extends the temperature range over which the liquid remains a liquid. So it increases the boiling point, it decreases the freezing point, and this is commonly used in antifreeze, like in your car, in your car radiator, if you have a car. Buses, I imagine, also use them. So this is used to make antifreeze. You can buy antifreeze like pre-mixed at the store, O'Reilly or wherever you shop for your auto goods. You can buy it pre-mixed, or you can buy just pure ethylene glycol or propylene glycol or whatever glycol you prefer, and then mix it yourself. If you don't mix it, it's not as good. You have to mix the water and the glycol together or it doesn't work as well. The two ends of this effect are called freezing point depression. Depression here being lowering, and boiling point elevation, or raising. If you add salt to ice, that lowers the melting point. That's why you add salt to your ice if you're making ice cream at home, like in the little experiment where you shake the little bag of milk or cream and it makes ice cream. We're not doing that, but you're welcome to look up videos and do that at home. if you'd like some ice cream. Okay, the first one up, freezing point depression. Freezing point depression, the concentration of the solution is usually expressed in molality, which is the lowercase m. So remember, big M was molarity, lowercase m is molality. They look very similar. They're both m's. We just swapped out one of the letters. Right? It's molality now instead of molarity. I don't particularly care for molality for reasons that I'll demonstrate to you momentarily. Our equation for molality is moles solute over kilograms solvent. Kilograms, the mass in kilograms of the solvent. I'm going to just say here it's the liquid, because it's basically the liquid. But it's the solvent, it's not the solution, and it's not the volume of the solution. I usually give you the molality equation on exams if it shows up, which it will. So kilograms of liquid, since our solvent is usually a liquid. So that's a little bit weird. Let's look at calculating molality. We want to calculate the molality, lowercase m, of a fructose solution containing 50.4 grams of fructose, sugar, and 0.332 kilograms of water. Molality equals moles solute, number of particles of solute, over kilograms of solvent. We have two chemicals here. We have fructose, we've got water. Which one is our solute? Which one is going here on top? You have a 50% chance if you're pure blind guessing. It's the fructose. And then the water is our solvent. We have grams of fructose, so we need to convert that to moles of fructose. 50.4 grams divided by our molar mass of 180 grams per mole. 0.279 and change moles fructose. So our molality, 0.279 ... moles fructose over our water that's already conveniently in kilograms, 0.332 kilograms. Our molality, 0.843 after we round, lowercase m fructose. I think the calculation part, relatively simple. Now, you may remember that for capital M, which is molarity, we just chop off the ITY. So for example, if we had 1M, it would be a 1 molar solution. We do the same thing for molality. We chop off the ITY. So molality, chop off the ITY. So if we have 1 lowercase m, this would be 1 molol. And that's why I don't like molality, because I don't like the way that molol sounds or feels. So this would be 0.843 mole solution. Try saying that sometime in your own time, I guess. Give it a say and find out that you also don't like it, maybe. Okay, so the reason that we learn about molality is so that we can talk about freezing point depression. It's one of our two colligative effects that we do calculations with. So the freezing point depression of a solution uses this formula, delta TF. This is the change in temperature, the delta for change, T sub F for temperature of the freezing point, and this is in degrees Celsius. So this is how much our freezing point is changing. How much freezing point is changing. Lowercase m is the molality of the solution, the one we just learned about, and Kf is the freezing point depression constant, K for constant. Kf will be given to you if you need it on an exam. Different solvents are going to have different Kf values. So really all that we have to do, there's a little bit of a trick. Basically all we have to do is calculate a molality, plug it into this equation. It's relatively hard to mess up. And then we get our freezing point. Okay, so let's look at an example of this. We want to calculate the freezing point of an aqueous 1.42 mole sucrose solution. For water, Kf is this 1.86 in a whole mess of units. But it's not actually a whole mess of units. It's just degrees Celsius per mole. Because mole solute over kilogram solvent is molality, so it's just the molality is flipped. So it looks like more of a mess than it is. So delta TF equals lowercase m times K sub F. We have Kf. We've got lowercase m. Plug it in. The molalities cancel. And our delta TF is 1.42 times 1.86, or 2.64 degrees Celsius. Questions? Is that our answer? What are we finding? We're finding the freezing point. Right? We're looking for freezing point, and it's an aqueous solution. What does aqueous mean? It means that we've got water as our solvent, as our liquid. What's the freezing point of water in degrees Celsius? 0. So our normal freezing point, normal FP, 0 degrees Celsius. What's the property that we're exploring called? It's not an English class, but I still believe that we can read. Freezing point depression. What is depression? Lowering, right? So if it's freezing point depression, we expect our freezing point to go lower. if our new freezing point is 2.64 degrees Celsius and our old one was 0 degrees Celsius, then that means that our freezing point has gone up. So I've laid a trap for you. Again, this delta TF, this is our change in freezing temperature. So our freezing point is changing by 2.64 degrees Celsius from 0 degrees Celsius. So our new freezing point is 2.64 degrees Celsius lower. So decrease the original freezing point by 2.64 degrees Celsius. So our new freezing point, we'll call it TF, is negative 2.64 degrees Celsius. Because we did 0 minus 2.64. There's not an equation for that. You also won't be given that the freezing point is 0 degrees Celsius for water. You're just expected to know that. Who likes déjà vu? All right, the other colligative property that we have that we're exploring, one of the other ones, is boiling point elevation. So the boiling point of a solution containing a non-volatile solute, something that doesn't evaporate quickly, is higher than the boiling point of the pure solvent. And this is a big part of the reason that antifreeze is used, particularly when it's really hot. It raises the boiling point in the radiator of the car and prevents it from boiling over and your engine from overheating. Now here's that déjà vu. Boiling point elevation has this formula. Delta TB, where the delta is changed and the B is for boiling, the T is for temperature, equals M, molality, times KB. KB is the boiling point elevation constant, K for constant. Different solvents have different values of KB, and you will be given KB if you need it. So it's almost identical to our freezing point depression, but we've swapped out the F's and put in B's. So B's instead of F's. Otherwise, it's almost identical. All right, I'm going to give this one to you to try. What is the concentration in molality of an aqueous sodium chloride solution with a boiling point given here? And the KB value is there. Remember that that is degrees Celsius per molal. So delta TB, not tuberculosis, is M times KB. See if you can find the concentration. All right, we are finding concentration in molality. Molality gets the symbol lowercase m. So we're finding lowercase m. We need to do a very little amount of algebra. So we're going to divide both sides by KB. The KB disappears from the right side, and we get M equals the change in tuberculosis divided by KB. Do we have KB? Yes, we have KB. Do we have delta TB? Do we have delta TB? What's the delta mean? Change. Delta means change. Do we have a change in boiling point? No, we don't. We have TB. If I put the decimal place in the correct spot, it looks like this. Degrees Celsius. This is TB. That's our boiling point. We want our change in boiling point. How our boiling point changed, in this case, how it went up, boiling point elevation. Because boiling point elevation. B for boiling. What's the normal boiling point of water in degrees Celsius? It's 100. So how much did our boiling point change? It is 101.78, because that's our new one, minus our old one, 100 degrees Celsius. Our boiling point went up 1.78 degrees Celsius. That's our delta TB. So our molality is 1.78 degrees Celsius divided by 0.512 degrees Celsius per mole. The degrees Celsius cancel. M flips to the top. 1.78 divided by 0.512. This is a 3.48 molal sodium chloride salt solution. If you did not do a change in boiling point calculation, then you would have gotten a concentration of like 200 molal, which is way too high. You'll never have concentration units that are in the 200 range. Okay, and then the last stuff that we'll talk about, I know that we're over time, is osmosis. Osmosis describes the flow of solvent, liquid, from a less concentrated solution to a more concentrated solution. The goal is to balance the concentrations. So osmosis occurs in situations where you have a semi-permeable membrane, like cells in your body have semi-permeable membranes in them, or in certain types of filters. So we've got a semi-permeable membrane here. We've got 0.1 molar on the left, 1.0 molar on the right. Our liquid is going to flow, our water is going to flow from this 0.1 molar side to this 1.0 molar side until the concentrations are equal or there's too much pressure that it can't flow anymore. You may have heard of reverse osmosis water filtration. It's this process, but backwards. So you just push on the water really hard to force the water through your little filter. This represents the osmotic pressure of the solution, which has the symbol pi. We're not going to do anything with that. I'm just mentioning it. So osmotic pressure is also a colligative property. It depends on the concentration of the solute particles, not on the type. If you've got a more concentrated solution, you're going to have a greater osmotic pressure, meaning that the water will rise further if it's allowed to. And this also shows up in living cells because they have semi-permeable membranes. There are 3 different situations that can arise, and we're going to use red blood cells as our example. This is relevant if you're getting saline at the hospital. This is why there's a very specific concentration of saline that you get if they're just trying to hydrate you. So we've got isotonic solutions, iso meaning the same, and tonic, we're talking about the concentration. So if it's isotonic, that means the solute concentration in the surrounding fluid is equal to that within the cell. So this is the same salinity, same concentration. And this is typically what they will give you at a hospital if you're getting IV fluids. They'll give you normal saline, it's isotonic, and that lets water move back and forth as necessary. It also distributes water throughout your body, but it's not going to force water into your cells or pull water out of your cells. If they were to give you a hypotonic solution, a lower concentration solution, then what would happen is your blood cells would now be more concentrated, and the water would try to flow into your blood cells, and that could cause your blood cells to swell, or even if it's really extreme, to pop, which obviously you don't want. So if you put pure water into your veins instead of normal saline, this is sort of what could happen. There are situations where hypotonic saline can be administered. There's also hypertonic, hyper being more than or higher. So this is higher concentration fluid, and this is going to draw water out of your cells and cause them to shrivel up and look really spiky and jagged. There are also instances where hypertonic saline might be given, but typically you're just going to get isotonic saline. And that's all that I have to talk about.